solutions look like. Alright, so if we have this, and let's say we want to find a solution that looks like y equals to sigma n equals to 0 to infinity of an x minus 1 to the nth power. And because x equal to 1 is a regular point of this differential equation, there must be a power series solution like this. Not regular, sorry, ordinary. I keep messing up. So the correct terminology is 1 is an ordinary point because if you divide by x squared, you get y double prime minus 1 over x squared, y equal to 0. And this coefficient function is well defined as continuous at x equal to 1. So it's an ordinary point. Okay? So this is an ordinary, x equal to 1 being an ordinary point. We know that such a power series solution does exist at x equal to 1. Now, let's differentiate. And see that I started with n equals to 1 like before. That's because if n is 0, 0 going into here will make everything 0, so there's no point in having n equal to 0, so I made it n equal to 1. And then y double prime is sigma and from 2 to infinity for the same reason. If n is 1 over 0, it disappears. So that's what you get. And now we plug this into here, and let's see. Oh. Okay, so that's going to be a lot more complicated than I thought. Okay. Well, let's plug it in and let me show you what's going wrong here. So if I have x squared sigma n from 2 to infinity n minus 1 an x minus 1 n minus 2 plus minus sigma n from 0 to infinity an x minus 1 to the n equal to 0. Okay, so that's what I get if I plug these into the differential equation. Now the trouble I'm getting right now is that if I move the x squared inside, then x squared cannot be multiplied to this because they have different bases. So in order to compute further, I need to figure out how to rewrite x squared as x minus 1 squared plus something x minus 1 plus something. I need to figure out what goes in there. And I think this should be 1, this should be 2. And that should be right. Let's just check. X squared minus 2x plus 1, that's what you get. This is plus 2x minus 2 plus 1. They cancel. 1 minus 2 plus 1, that's all 0, and you get x squared equal to x squared. So this is indeed true. Now, how did I get this so quickly? Oh. I mean, there's some things that I know that you don't, so I got it really quickly. But if you wanted to figure it out on your own, here's what you do: just put it as a and b. And this is a functional equation, meaning they're equal as functions. So they should equal for any value of x, right? So one way to do it would be plug in x equal to 1, and you get 1 on the left side, but you get 0, 0, and b. So you get b equal to 1 immediately, right? And then just plug in another number, x equal to 0. What does that give you? 0 equal to 1 minus a plus b. And then since b is 1, you solve for a, you get a equal to 2, right? Good. So that's how I got a equals to 2 and b is 1. And after that, just verify that what you wrote does hold true just by expanding everything and simplifying. Okay? All right, so we got that. And I like it because now I can rewrite this as x minus 1 squared plus 2 times x minus 1 plus 1 times sigma n equals to 2 to infinity n minus 1 an x minus 1 n minus 2. I don't want to copy everything, but if I don't, it's going to confuse everyone. So this is what I did. I replaced this x squared by what's on the right. And then, now I like this because now I can multiply this, right? So you're going to get 3 sigmas. And here's what you get. You get the first sigma is sigma n equals to 2. No, let me not write. The first one is x minus 1 squared multiplied to this sigma. The second one is 2 times x minus 1 multiplied to this sigma is equals to 2 to infinity n minus 1 an x minus 1 x2 plus 1 times sigma n equals to 2 to infinity n minus 1 an x minus 1 and minus 2. And finally this thing plus, no, minus sigma n equals to 0 to 0. So you have a total of 4 terms. It's a lot. And let's continue. I need to use a different color so I can know which one's which. Alright, so now this thing can go inside, and because now x minus 1, they match, I can put them together, right? That's the whole purpose of trying to put it into this form. If I write everything in terms of x minus 1, I can do that, right? So I have sigma n equals to 2 to infinity. The first term is n, because 2 plus n minus 2 is just n. Right? And then the second one is first I would need a 2 here because 2 went inside. And this, what should I put here?
N minus 1.
N minus 1. Because this is first power 1 plus n minus 2 is n minus 1, so that's what I get. The third one is, well, there's nothing multiplied to it, so this is this. And then minus that last thing which never changed. I still have to write it so that I don't confuse myself. So that's what I get once I plug everything and sort out in terms of x minus 1. Then now I see what I need to shift. Which one should I shift? The second term, this one I need to shift, right? And this one. Right? These two I need to shift. These two are okay because they both have x minus 1 to the nth power. These I need to shift. So let's shift it. So first of all, for this one, in order for this to be n, I need to replace n by n plus 1. So n plus 1 equals to 2. Solving for n, what do I get? N equals to what? 1 to infinity. And then 2 times n plus 1 times n, a n plus 1, x minus 1 to the nth power. Right? That's what you get after shifting. What about this? What should I do?
N plus 2.
Yeah. And then if I say n plus 2 is equal to 2, I get n equals to 0. And I get n plus 2, n plus 1, a n plus 2, x minus 1, the nth power. And the other two, I don't need to shift. So let's just copy the other two. Okay. Now I have to take those things that are manufactured before other things are manufactured as a separate thing. When n is equal to 0, these two produce something, right? What does that give us? When n is 0, I get 2 times 1 times a2. So it's 2a2. X minus 1 to the 0th power doesn't give you anything. Anything to the 0th power is 1, so there's nothing there. And if I plug in 0 here, it's a0, and again, this is just 1, so I get minus a0. That's what you get for n equal to 0. Okay. Plus, when n is 1, now these three factories are in the manufacturing phase. So let's write everything. So when n is 1, 2 times 2 times 2 times 1, which is 4, a2. 4a2, yes. And x minus 1 to the first power. I'm going to put x minus 1 to the first power outside because I know that that's going to be common for everything. And when n is 1, 3 times 2, that's 6a3. So 6a3. And then here, when n is 1, it's minus a1. Okay?
What's that first number,
Do you have a question?
Oh yeah, next to the 4, is that an A2? Like, no, right there.
4a2, yeah, this should be a2.
Thank you.
Okay, and then starting, so that's n equals to 1 and afterwards. That's just n equals to 1. And then starting from 2 and afterwards, all of them are manufacturing terms at the same time. So n equals to 2 to infinity. Now it's this, all of them put together. And let's see, this is, and these two can be put together, right? Let's write these two first. It's a huge term. n minus 1, an minus an. So I put this right afterwards because I want to put them together. And then plus twice of n plus 1 and an plus 1 plus n plus 2 n plus 1 a n plus 2 times x minus 1 to the n. That's what you get. So that's the summation. It's the big summation. Okay. And from this, now we can solve like before. Each of these are 0. This should be 0. This should be 0. All the coefficients are 0, right? So let's write out what that means first. So that means 2a2 minus a0 is 0, giving you that a2 is equal to 1 half of a0. If I move this to the other side and divide by that, plug that. And for this one, I have 4a2 plus 6a3 minus a1 equal to 0. And that one, always you solve for the highest order, highest index. Index 3 is the highest here. So if I solve for 6a3, so a3 will be a1 minus 4a2 over 6. So those are the two special cases in the beginning. But after 2 and above, you follow the pattern. This is what you get, right? So after that, go over here. After that, we have n minus 1 minus 1 an. So see, these are common, so I factored it out. And then plus 2 n plus 1 n a n plus 1 plus a n plus 2 n plus 1 an plus 2 equal to 0. That's what has to be put to 0. And from here, this gives us the recurrence relation. So we solve for an plus 2, and that gives us the recurrence relation. So how does that go? That's n plus 2, n plus 1, an plus 2 gives you minus of this entire thing. By the way, this is n squared minus n minus 1, right? N squared minus n minus 1, an plus 2, n plus 1 n, an plus 1. Since both of them were brought to the other side, they both got the minus sign. And finally, you divide by this, you get an plus 2 equal to negative n squared minus n minus 1 an plus 2 n plus 1 and an plus 1 divided by n plus 2 n plus 1. So that's true for n greater or equal to what? 2. So everything works out, as you can see. We found the first a0 and a1 are free variables. a2 is this, a3 is this, and if we wanted just one more to get 5 non-zero terms, we just have to plug in 2 here, which gives us a4 equal to, let's see, 4 minus 3, this is a2, plus if I plug in 2, 4 times, 6 times 2, 12, a3 over 4 times 12. But then a3 is this thing over 6, right? So if I plug this in over here, and also a2 is 1 half a0, so if I plug them in, oh, you know what? I should have done more here. See, a2 is 1 half a0, so it's a1 minus 2a0 over 6. That's what a3 is. And then if I plug those two here, I get minus 1 half a0 plus twice of a1 minus 2a0 over 12. The reason I get 2 is because 12 divided by 6 gives you 2. That's where I got this 2. And then if I further simplify it by dividing and multiplying 2 top and bottom, I get minus a0. Let's see. 4 times negative 7 a0 plus 8 a1 over 12. That's what I get. And therefore, finally, if I write down the answer for this differential equation, let's say we're writing down the first 5 non-zero terms of this differential equation. It turns out that it's y equal to a0 plus a1x plus 1/2 a0. Oh, I messed up, right? It's not a power series around x, it's a power series it's a power series for x minus 1. And then plus a1 minus 2a0 over 6 x minus 1/3 plus, if I multiply the minus, you get 7a0 minus 8a1 over 12 x minus 1/4 plus da da da. Okay? And if you continue this process, you can get more terms. And given your initial values at, by the way, in this case, you would see that y of 1 is really a0, and y prime of 1 is a1. So if you control these two initial values, then you can know all the coefficients. And if you know more and more coefficients, definitely you can find the approximate value of the function for any case. So that's how you solve by a power series centered around an ordinary point other than 0. It's more complicated.